Dear friends, we are in the first unit, representation of multi-dimensional arrays and their address calculation. Address calculation of a particular element within a multi-dimensional arrays. We are going to consider a two-dimensional array. All right, let's have a look. Consider a two-dimensional array of size 3 rows, 4 columns. So a two-dimensional array, let's call it A, and we will have values. So you will have total values of 12, 4 into 3. So, and how are they going to be represented in the computer memory? That's important. This is often a theoretical question. Now when we have an array, though an array looks like a table in two-dimensional paper of rows and columns, the computer memory is linear. So how do we represent an array? So commonly there are two methods used to represent a two-dimensional or a multi-dimensional array into memory. One is called a row major order and the other is called a column major order. So when we need, for example, if it's an integer array of so many items, so it will reserve so many locations required here, for example, 4 into 3, 12, and as many bytes required as each item is, so many memory contiguous locations will be reserved and the array will get represented. So how do we represent? Now in both representation, when we have here, for example, we will need 12. Let's consider this as an integer array. So we will have 12 locations, each of 2 bytes reserved, and each representation will have what is called a header details. This will tell you what is the lower bound of the array, what is the upper bound of the array, what is size of each item, what is the starting address, which is called the base address, etc. So all that will be explained in the header details. Now if I use the row major order, now we can consider this two-dimensional array are a sequence of 3 linear single-dimensional arrays. So we have first array, second array, a third array. So in a row major order, what is going to be done is each array is going to be represented row wise. So we take the first row, so that is explained, stored here with all the 4 elements of the column. So, and then we have the second row again stored sequentially and the row items. So this way row items will get stored one after the other, and the third row, the 4 elements in the column. So this is called a row major order. Okay. And the other, what is called a column major, what happens is we are going to represent items column wise. So here we know we have 4 columns, okay, and each column consisting of 3 row items. So each column is represented. So here we had only totally 3 rows, okay, and here we have 4 columns. So let's say the first column is 3 items. So this is our first column represented of 3 items, and the second column, so represented from here to here, third and fourth. Of course, as usual, the header file will consist of all the information basic to the array: size, base address, lower bound, upper bound, starting address, etc. So this is how multidimensional arrays are represented linearly in a computer memory. This is an important question. Along with it also comes what is called address calculation. Now, given a two-dimensional array, how do I perform if I want to find out the address of a particular location, thereby, let's say, the content of the array? Now, let's again consider the same array, 3 into 4. So, how do I calculate the address of a particular item within this memory representation using what is called the linear representation within the memory, either be it in row major or column major. We will see here the row major, the column major. I think you should be able to arrive at thereafter. So it's a two-dimensional array A, and there are 12 items. Now we know that let a general rule be taken. We have a multidimensional two-dimensional array having R rows and C columns, and each item, let the size be E size in bytes. Okay, so we have R rows, C columns, and each item is of C size. We know in a base memory representation, the starting address, the first item, is always called as base address. So let's imagine for this two-dimensional array, the starting address or the address of the first item is base A. No? That is the first item. That is address of, if you use a C representation, A11, address of the first item. Okay. Now, if I want to find the address of the ith row, no, I can be anywhere. Okay, suppose I want to find out the address of, so this is, if I use a numeric representation, this is the first 0th row, first row, so this is second row here. So what would be the address of the ith? The second row, it would be base address, that is this, plus, so we have to transfer how many rows? 2 rows. 2 rows, each of C items, okay, and each is of E size. So base address plus I into C into E size, that will be the address of this item, and the value at that address will be the item. So this is the first item in the ith row. So this is a common formula. Now, having done that, suppose I want to, let's say, find the address of an ijth row in the multidimensional array. So let's say this is the I and jth item. So this is, if you look 0, 1, 2 representation, this is the first row, okay, first row programmingly in C, and this is the second column. Okay, so how do I do this? So we know, so if I want to reach ith row, so that is this, so I will have to go I times into C. Now jth item, let's say if this is a jth item, that means I need to again traverse j times, correct? Okay, so I rows of C items, then I need to go j. That means I rows, so it comes here, then to reach here I need to go j items. So the address of the jth item would be base address, starting address, okay, first item, plus, okay, so I times C plus j, and each of is E size. So E size into I into C plus. So this gives you the address calculation for an I comma jth item in the two-dimensional multi representation of an array. Similarly, for the exam, it's also important to explain the column representation. Same, logic is same, only difference would be in the formula that we will leave to you, E size. So how many columns to traverse, and each column of how many items, so values will change. Okay, I think you should know from this formula, we will leave it to you. So this is a common representation address calculation, a very important question, theory question in the first unit. Thank you.